Everyone. In this video, we're going to look at one of the problems from mathematical induction. And the problem is as follows. An odd number of people stand in a yard at mutually distinct distances. At the same time, each person throws a pie at the nearest neighbor hitting the person. Okay, so the throwing of the pie is kind of controlled by this constraint that each person each person throws a pie at their nearest neighbor. And what we also know is that the distances are mutually distinct. Okay, so use mathematical induction to show that there is at least one survivor, and that is at least one person who is not hit by the pie. So the definition of a survivor in this question is that person who is basically not hit by the pie. Okay, so one of the first things that we did in the lecture was to define the proposition. The proposition over here is that that when you have these odd number of people in the yard satisfying the constraint that there are mutually distinct distances, and each person is throwing a pie at the nearest neighbor, you'll at least have one survivor. It's basically restating the problem. So, given a proposition P where we restate the problem, let's try to think about the bases. What is the basic step in this mathematical induction? Okay, so if I draw these two columns over here, okay, where the first column is just basically the integer n, okay, and then on the second column, what I have here is the number of people that are participating in this game. Okay, so let's make this thing clear that n over here does not represent the number of people. N is just an integer. It's just an integer that happens to be n is greater or equal to 1. It's just an integer that happens to satisfy that n equality. Okay, so what does this mean here? It means that n can take on values 1, 2, 3, 4, and so forth, going up to positive infinity. Now, for every value that n takes on, over here, what is the connection that I can use to connect n with the number of people in the game? Well, if I use a formula where the number of people in the game is equal to 2n plus 1, then I can see that when n equals to 1, and I plug in n equals to 1 into this expression, what I get back is a value 3. So I can think about this way, but the number of people in the game needs to be odd. So when n equals to 1, I've got three people playing this game. When n equals to 2, when I plug in n equals to 2 in this game, I get into this expression, what I get back is 5, 7, and so forth as I keep on going down. Okay, so everything in orange over here represents the number of people, and here the first column n just happens to be an integer. So now when I come back to my proposition, instead of saying p, I can say this. Let's define a proposition in terms of this integer p of n. Okay, so what should the basis be? Well, the basis over here is the first element. Is the first element in this in this table. So p of n, where n is just this integer that goes from n is greater or equal to 1. My basis is it true? Do you have one survivor? Do you have one survivor in the game when n equals to 1? Well, n equals to 1 represents I should have at least 3 people, well, exactly 3 people playing the game. So when I have 3 people playing the game and I draw these 3 people over here, 1, 2, and 3, and again, just to be a little bit clear, let's assume that the third person is over here. And as per definition, because A and B are closer to each other, A is going to throw a pie at B, and B is going to throw a pie at A. Okay, and person C over here is going to throw a pie either at B or A, depending on which of these distances is closer from C. So let's assume that B is closer to C, so C ends up throwing a pie at B as well. So I can see my basis that there is one survivor, and the survivor happens to be person C. So here is my survivor. Okay, so I can see that it has been proved for P of 1. Okay, this is done. Okay, now let's look at the inductive step. Okay, so for inductive step, what I'm looking at is basically I have this statement that for all k, the conditional statement of P of k, if P of k, then P of k plus 1 must hold. Okay, so this entire conditional statement must be true. Everything in the box over here must be true. It must be true for all k. Okay, if the box must be true for all k, then what I can also say from here is that let's assume let's assume that it's true for p of k. Let's assume that p of k is true. Well, if p of k is true, if p of k is true, then for this box to be true for all k, okay, and I'm choosing this k a completely an arbitrary number. I'm just assuming that p of k is true. If p of k is true, then I must show that p of k plus 1 is also true. Okay, so the assumption here is that p of k is true. And with this assumption, I need to show whether p of k plus 1 is also true. Okay, so let's show this. So what I'm going to do now is I'm just going to erase portions of this of my blackboard here. So I'm just going to erase these things over here, and let's say for some arbitrary k. Okay, so k is over here, some arbitrary k, right? This is just an integer. This is just an integer. This is just some integer. So for some arbitrary k here, how many people are playing this game? Well, if it's k, the number of people playing the game is going to be 2k plus 1. And I already know p of k is true. So let's say this entire orange box represents the number of people, which is 2k plus 1. This is 2k plus 1, the number of people actually playing the game. Okay, and again, this is for the expression p of k, but I know it's true. Okay, so I've got these 2k plus 1 people in there. Okay, I'm just drawing them arbitrary right now. Okay, when I add these guys up, they'll all be equal to 2k plus 1. And we are assuming that p of k is true. Okay, now let's show whether p of k plus 1 is actually true. So everything in yellow now is for p of k plus 1. To show that p of k plus 1 is true, okay, so there's some k plus 1 over here. Okay, how many people will be playing the game if n equals to k plus 1? Well, if n equals to k plus 1, and if I plug in over here k plus 1, what I get back is 2k plus 3, right? I'm just taking k plus 1, and plugging it into this expression. So I get back 2k plus 3. So I've got a total of 2k plus 3 people here. And what I'm going to do is I'm just going to divide them. I'm just going to divide them into not two equal halves, but into two halves, where this is 2 people over here. So from a total of 2k plus 3, 2 of these people over here, and and whatever is remaining, which is 2k plus 1, are over here. Okay. Now let's assume that these two are closer to each other. Okay, so which means that this person throws a pie over there, and this person ends up throwing a pie at this person because they are close to each other. Okay, and one other person over here, let's take this person over here. Let's take this person over here in green. The person in green happens to be closer to this person over here. Okay, so it happens to be closer, so this person ends up throwing a pie over here as well. Okay, so what this tells you is, so if I just again do a kind of a nicer division here. Okay, let's just kind of divide it in this way. Okay, so I have a total of 2k plus 3 people. I have a total of 2k plus 3 people. 2 of these people are over here. Okay, and the remainder 2k plus 1 are on this right hand side here. Now the number of pies that actually end up in this pink region, in this entire pink region over here, the number of pies that are thrown in this pink region were actually how many? How many pies were thrown there? So I do know that one of the pie ended up over here, which is in green, and there are a total of 2k plus 1 people in this pink region. In this pink region, there are a total of 2k plus 1 people. Each one of them had a pie to begin with. But when the game started, one of the pie in green crossed over and hit this person over here. So the number of pies that ended up being thrown in this pink region, right, and none of the yellow pies ended up crossing it into the other half, is that 2k pie were thrown in the pink region. So if I had 2k plus 1 people, and 2k pi were thrown in that region, I can see that this number over here is greater. And if the number is greater, that implies there is at least one survivor, one survivor in this entire circle in yellow, which implies that P of k plus 1 is actually true. I did show you that to express it whether P of k plus 1 is true. It is true because there because in this pink half there were a total of 2k pi thrones, from which there happened to be 2k plus 1 people, meaning there is at least one survivor. But now if you tell me what happens if there were many pies thrown, let's say this person over here also happens to be closer to this person over here, so this person ends up throwing a pie over there as well. Well, that's okay, because that also implies that if there were many pie thrown at these two individuals, that would still imply that there were less pie thrown in the pink half. And because if there were less pie thrown in the pink half, it would imply that there are more survivors. There are more survivors in the second half, which should again validate the claim that there is at least one person who is not getting hit by the pie in this half of p of k plus 1. Okay, but what happens if there is zero pi, if there's zero pi thrown in this half here? Let me kind of redraw this universe again. So let's come back. Let's redraw this yellow thing over here. And now I still have my two people here, person 1, person 2, and everybody else 2k plus 1 is over here. Okay, and I also know that this person throws a pie at this person over here, this person throws a pie at the second person here, and there is no crossing. There is no crossing of pies being thrown at either. There's no crossing of pies across this yellow line. So if you have a total of 2k plus 1 people here, the number of pies that were thrown in this half is also going to be 2k plus 1. Okay, and over here you've got two people, and the number of pies that are thrown over here is also exactly 2. Okay, so now what's interesting here is that I do know this person's not a survivor. This person's not a survivor either. Okay, what about this half here? Is there any survivor in this half here? Well, this half over here represents a total of 2k plus 1 people. If it represents a total of 2k plus 1 people, this means that this piece over here is basically an expression for P of k. It's an expression for P of k. And here's the key: because 2k plus 1 people represents as an expression of P of k, and I've already assumed in my assumption that we're going to assume that P of k is true. If P of k is true, then that implies that there is at least one survivor, because that's the assumption I started with to show you whether P of k plus 1 is also true. Okay, so because this is true, I do know that there is at least one survivor in there. There is at least one survivor. My handwriting is getting terrible over here, but at least I'm using my audio, so you can at least hear me say this, that there is at least one survivor in this half. That's the assumption that I started with. So with this we finish a mathematical induction where we have shown that the expression P of k plus 1 is also true when P of k is also true. And now, because I know that P of k plus 1 is also true when P of k is true, and I know that the basis is also true, the moment I take my basis, which is P of 1, and plug in over here, I chose k to be completely arbitrary, but now when I plug in P of 1, when P of 1 is true, I will know that P of 2 must also be true. And because P of 2 is true, then I know that P of 3 will be true as well, and so forth, until I can show you that this is true for all n. And n, again, remember, is just an integer. Because it's true for all n, meaning it's true for every single value in the first column, I can then show you that it's also true for every single value in the second column as well, because the connection between the second column and the first column is simply 2n plus 1.